Okay, so here's the question. Starting off with the schematic, you can see the pool is over here. Um, the top surface, the inner surface of the plate, the bottom surface of the plate, and the saturated water. And the velocity going parallel. So at 1 atmosphere, the saturated temperature is 100 degrees Celsius. That's the water temperature. Um, so these are the assumptions: steady state. Negligible heat losses from the plate or like the also the edges of the pool, and constant thermal properties, constant convection heat coefficients. Going to neglect radiation, and all the heat will from the convection is going to go up into the plate. So for part A is to determine the boiling heat transfer rate. So gonna start off with getting the convection heat transfer rate. So start off with the film temperature, which is going to be the air temperature plus the bottom temperature over 2, so that's at 600 C. So use table A15 to get all these values, the density, conductivity, viscosity, and Prandtl number. So with that, get the Reynolds number. So this is 31,000 about, so that's going to be laminar. And with that external flow, you can use this equation to make sure these two are right, and get the Nusselt number, and then solve for H. So with this H, we can get the Q. So Q will be H, and the temperature of the air and the bottom. So the total convection Q will be 6,262 watts per meter squared, and it'll be the same for the total rate, just watts, because it's just one meter length. So, and the Q boiling is going to be equal to the Q convection, because the all the heat from the convection goes into boiling, stated in the problem. So that's that. So for part B is to determine the temperature of the top surface of the plate. So we're gonna assume that the bottom temperature of the surface temperature of the inner is equal to the bottom temperature, just for an assumption. So that'll give you an excess temperature of 10 degrees. So this will be between 5 and 30, so we can assume nucleate boiling regime. So yeah, look at this graph here. So yeah, that'll be in the nucleate regime. So yeah, after this, well, you can use this equation here for the T-excess, and with all these values. So these will be found at the saturation temperature, 100 degrees. So yeah, I found it from this table A9, and here they all are. As well as this one from a couple other tables. This one is from, this one's a different table, and this one is a different table as well. But yeah, I just can calculate all these, put that into the equation, and I get a excess temperature of 3.59. So it's a bit different. It's a different from the assumption of 10, but yeah. So the TS, so that the inner surface is going to be 103.6 degrees Celsius or about. So this result makes sense. 3.59 is low, but that's because our Q was also very low. It was only 6,262 or so. So this would be like here. So it kind of makes sense that it's not, because here this starts, it'd be like down here somewhere. So this makes sense. So it's not a very strong Q boiling, which is why it's not. It makes sense with that number. And I guess that means the water is, the force of the saturated water is much stronger. And also, the Q boiling, the difference is 6.4 degrees between the top and bottom of the plate. So I guess that confirms it's a very thick plate, because copper is a pretty good conductor. So 6.4 degree change means it's very thick. So yeah, for part C, it's examine the impact of the assumptions. So steady, this one, assumption's fine, negligible losses should be fine, constant thermal properties, constant convection is fine, but this is the big one, neglect radiation. That assumption is probably not valid, because the air temperature was like 1090 degrees Celsius. That's a really massive number, so there probably is certainly like radiation as well as for convection. So that's a big one. The rest of them are okay. And also there's another assumption. So this was 3.59, so that's actually below this other assumption. So it's actually more within the natural convection boiling, not really a nucleate boiling. So maybe this equation isn't perfectly accurate either. Okay, thank you.